Right now, as you listen to this video, more than half of every machine humanity has ever sent to the surface of Mars lies broken across its red plains. Wreckage from 4 space agencies, 60 years of attempts, a failure rate that would ground any airline on Earth within a week. And the cruel truth is that Mars is not getting easier to land on. It is getting harder for reasons most people have never been told. Tonight, you're going to descend through the most dangerous 7 minutes in human exploration. The physics, the failures, the desperate engineering, and the fundamental planetary trap that makes Mars so treacherous. And understand why the world that looks so close on a telescope keeps destroying everything we send. Before we dive in, if you love space exploration as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. Now, let's begin. There is a planet in our solar system that sits in what astronomers call the habitable zone. It has a solid surface. It has an atmosphere. It has polar ice caps, ancient river valleys, and a day that lasts almost exactly as long as a day on Earth. For a century, humans looked at this planet and felt a deep, almost instinctive pull. It was close enough to see surface features through a backyard telescope. It was cold, certainly, and dry, and the air was thin. But so are the high flanks of Everest, and people climb those. Mars, the story went, was the next step, the achievable horizon, the second Earth that wasn't quite a second Earth, but was close enough to be worth reaching for. That story is not entirely wrong. Mars is reachable. Mars has been reached. But reaching it and landing on it safely are 2 problems so different in character that they barely share a vocabulary. And the gap between them has swallowed spacecraft, careers, national programs, and billions of dollars, over and over, across 6 decades of trying. Roughly 60% of all spacecraft ever destined for Mars have failed before completing their missions, with some failing before their observations could even begin. That number improves considerably when you isolate the modern era. The last 2 decades have seen far fewer catastrophic losses, but it disguises something important. The missions that succeeded in recent years succeeded because they were extraordinarily well-funded, obsessively engineered, and almost cosmically fortunate. They did not succeed because the problem became easier. They succeeded in spite of the fact that, in certain fundamental ways, the problem is getting harder with every kilogram of payload we try to land. To understand why, you need to understand something about Mars that most casual observers miss entirely. Mars is not simply a difficult destination. Mars is a planet that is difficult in a very specific, almost engineered way. It occupies a physical sweet spot where every technology we have developed for landing spacecraft is pushed exactly to its operational limit and no further. Not comfortably below the limit, where there is margin for error. Not beyond the limit, where the impossibility is obvious and forces a different approach. Exactly at the limit. That sweet spot, that precise zone of maximum engineering difficulty, is not an accident of bad luck. It is a consequence of Mars's mass, its position in the solar system, and the particular composition of its atmosphere. It has been waiting there, unchanged, for 4 billion years. And it will keep waiting. Take stock of where we are before the details arrive. We are standing, in imagination, at the beginning of a story that has been told in real time across 6 decades by engineers who poured the best years of their working lives into solving it. Some of them succeeded, triumphantly. Many of them failed. And all of them, successful or not, returned from the experience with the same message. Mars is harder than it looks. Mars is harder than you think. Mars is harder than the math suggests it should be. And when you understand exactly why that is true, the success stories become more extraordinary than they appeared before, and the failure stories become something other than embarrassing. They become, in a strange and sobering way, almost inevitable. This is where we begin. Not at the moment of descent, not at the 7 minutes of terror that have become the phrase attached to every Mars landing attempt. We begin earlier than that. We begin with the planet itself, with what Mars is and what Mars is not, and with the specific way that the universe constructed this world to be just difficult enough to keep breaking things. Mars is the fourth planet from the Sun, orbiting at an average distance of roughly 228 million kilometers. Its diameter is about half that of Earth. Its gravity is roughly 38% of what you feel right now, listening to these words. Its year is approximately 687 Earth days long. It has 2 small moons, Phobos and Deimos, captured asteroids that circle it at low altitude, and its surface is a landscape of extraordinary geological variety. Towering shield volcanoes, an enormous canyon system called Valles Marineris that would stretch across the continental United States, ancient cratered plains, and smooth lowland basins that may once have held standing water. All of that is the surface of Mars. What matters for landing is what stands between a descending spacecraft and that surface, the atmosphere. The Martian atmosphere is composed primarily of carbon dioxide, roughly 95%, with small amounts of nitrogen and argon and trace quantities of other gases. This sounds vaguely similar to Venus, which also has a carbon dioxide atmosphere, and to early Earth, which passed through phases dominated by carbon dioxide. But the similarity is purely chemical. The physical character of the Martian atmosphere is nothing like Venus and nothing like Earth, and that difference is the central fact around which every Mars landing attempt has been organized. Mars's atmosphere has less than 1% of the density of Earth's atmosphere. Unlike Earth, where atmospheric entry is heavily reliant on atmospheric friction to decelerate and manage re-entry heat, Mars's sparse atmosphere provides significantly less resistance. That single fact, 1% density, sounds abstract until you follow its consequences into engineering reality. And then it becomes the most important number in the story of Mars exploration. On Earth, when a spacecraft or a meteor or a returning capsule enters the atmosphere, it encounters a dense wall of molecules. Those molecules resist the incoming object. They compress against its leading edge, heat up dramatically, and transfer that heat into the object, which is why returning space capsules need heat shields. But they also slow the object down. They drain its kinetic energy. A capsule entering Earth's atmosphere at 8 kilometers per second will, by the time it reaches the lower atmosphere where parachutes become useful, have shed most of that velocity through aerodynamic drag. The atmosphere does most of the braking work for free. On Mars, that braking work barely happens. A spacecraft enters the Martian atmosphere at roughly 6 to 7 kilometers per second, traveling on an interplanetary trajectory that has been built over a journey of 6 to 9 months. The thin atmosphere does resist it, generates a heat shield temperature of roughly 1,600 degrees Celsius at peak heating, and slows the spacecraft down, but it slows it much less. Because the Martian atmosphere is roughly 1/100th the density of Earth's, entry vehicles tend to decelerate at much lower altitudes, which gives much less time for the subsequent landing events. By the time a spacecraft has dropped low enough for a parachute to deploy, it is still traveling at supersonic velocity, often faster than the speed of sound on Earth, sometimes close to twice that speed. This is the first problem. The atmosphere is too thin to do the braking job on its own. The second problem follows immediately from the first, and it is subtler and more treacherous. The atmosphere is also too thick to ignore. That sounds like a contradiction. How can an atmosphere be simultaneously too thin and too thick? Here is the answer. Too thin means it cannot slow a spacecraft down enough for a parachute to work efficiently at high altitude. Too thick means it is dense enough to generate enormous heat during entry, heat that requires a heavy, engineered heat shield to survive. If the atmosphere were even thinner, say as thin as the Moon's near vacuum, spacecraft could skip the heat shield problem entirely and use only rockets to slow down. If it were thicker, say as thick as Earth's or Venus's, the atmosphere would do most of the braking work and parachutes would be highly effective. Mars sits in neither camp. It sits in between, where you need a heat shield because the air is thick enough to cause serious heating, and you need rockets because the air is too thin to stop you, and you need parachutes to bridge the gap. And each of those three systems imposes its own mass penalty, its own complexity, its own new failure modes. Mars's atmosphere is dense enough to pose major problems for engineers, but it's still too thin for parachutes to fully slow down a plummeting lander. That's why you need an additional step of the landing sequence that helps soften the rover's touchdown. This double bind, the simultaneous too thin and too thick problem, is sometimes called the Mars atmospheric problem by engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, and at the European Space Agency's ESTEC facility in Noordwijk, Netherlands. It is not a solvable problem in the sense that it can be eliminated. It is a fixed constraint, as permanent as Mars's orbit. Every lander, every rover, every future crewed vehicle will face this same double bind. And the heavier the payload, the more acute the bind becomes. Pause here, because this matters before we continue. The mass scaling issue is not simply a concern for the future. It has already shaped the history of Mars landings in ways that are poorly understood by people who follow the missions at a casual level. Every successful Mars lander to date has been relatively light. The Viking landers in 1976 weighed roughly 572 kilograms each at landing. The Mars Pathfinder in 1997, carrying the tiny Sojourner rover, was lighter still. The Spirit and Opportunity rovers that landed in 2004 each weighed under 185 kilograms. The Curiosity rover in 2012 weighed approximately 900 kilograms, and landing it required the invention of an entirely new system that the engineering community initially regarded as somewhere between audacious and deranged. All successful United States Mars EDL systems landed at elevation sites below -1 kilometer, with landed masses of less than 0.6 metric tons. Before Curiosity. If a human crew ever lands on Mars, they will arrive in a vehicle that weighs not 900 kilograms, not a few metric tons, but potentially 20 to 40 metric tons. The atmosphere that barely stopped Curiosity will have even less ability to stop a crewed vehicle. The problem does not scale gracefully, it fractures. But all of that is the future. The present is challenging enough, and the present begins with a number that has become something close to famous in the culture of planetary exploration: 7 minutes. 7 minutes is approximately how long it takes a spacecraft to travel from the top of the Martian atmosphere to the surface. 7 minutes from 20,000 kilometers per hour to zero, or as close to zero as the landing system can manage. 7 minutes during which the spacecraft is entirely alone, because Mars is so far away from Earth that mission teams cannot communicate with the spacecraft in real time. The spacecraft has to guide itself. By the time engineers on Earth learn what has happened, the vehicle will already have been dead or alive on Mars for 7 minutes. That light-speed delay, currently ranging from about 3 minutes to 22 minutes each way, depending on where Earth and Mars are in their orbits, means there is no possibility of human intervention during descent. No course correction ordered from the ground, no last-second adjustment. The spacecraft must execute its entire landing sequence autonomously, following a pre-programmed script that the engineers wrote months before the mission arrived at Mars, based on atmospheric models that are necessarily imperfect, using systems that have never been tested in the actual Martian environment. Think about what that means in practice. Every calculation, every contingency, every sensor reading, every valve actuation, all of it must be anticipated and scripted in advance. If something unexpected happens, the spacecraft's onboard computer must diagnose the problem and respond to it without any human guidance in real time while falling toward the surface at hypersonic velocity. The software cannot ask for help. There is no one to ask. This is not a solvable problem either. It is a consequence of the speed of light and the orbital mechanics of the inner solar system. The EDL phase takes less than 10 minutes and occurs after a long journey of at least 6 months. During EDL, many complex processes, parachute deployment, thruster ignition, precision guidance, have to work perfectly and autonomously in a tightly synchronized manner, with no possible ground intervention. When engineers at JPL call this the 7 minutes of terror, they are not being melodramatic. They are describing a real condition of irreducible vulnerability that exists regardless of how well the mission has been designed, regardless of how many simulations have been run, regardless of how experienced the team is. The spacecraft falls, and you watch, and you wait, and you cannot do anything at all. Now take those two foundational constraints, the atmospheric double bind and the communication delay, and consider what they demand of the engineering team. They demand a system that can autonomously execute a precise, multi-phase deceleration sequence in an atmosphere that is simultaneously too thin and too thick, on a planet 200 million kilometers from the nearest human who might help, in 7 minutes, with no second chances and no recovery from a single critical failure. That is the baseline. That is what every Mars landing attempt has faced since 1971, when the Soviet Union's Mars 2 became the first human-made object to reach the Martian surface, by crashing into it at full speed, its parachute never having deployed. And that is what every future Mars landing attempt will face, for as long as humans continue to try. The history of that trying is a story of extraordinary ingenuity, stunning failure, and the relentless pressure of a universe that does not grade on a curve. The Soviet Union launched its first Mars mission in 1960. It never reached orbit. A second attempt that same year failed at the same stage. In 1962, 3 more Soviet missions failed in rapid succession, 2 in Earth orbit, 1 after launch. The year 1962 saw 5 attempts to reach Mars, and every single one of them failed before getting close. These were not close calls. They were complete losses, most of them before the spacecraft had even cleared the vicinity of Earth. This early wave of Soviet attempts is worth dwelling on for a moment, because it establishes something important about the character of Mars exploration that tends to get lost in the later, more polished narrative of technical sophistication. Mars has been defeating us from the very beginning. Not occasionally. Not in specific phases of a learning curve that eventually flattened. From the beginning and persistently, and with a kind of comprehensive thoroughness that engineers find both maddening and, in retrospect, instructive. The Soviets tried again in 1964. 2 missions. Both failed. In 1969, they tried twice more. Both failed. In 1971, they finally got spacecraft into Martian orbit, Mars 2 and Mars 3, each carrying a lander module. Mars 2's lander, released during a global dust storm that blanketed the entire planet in a haze that no radar could peer through, entered the atmosphere at too steep an angle. Its parachute never deployed. It became the first human-made object to reach the Martian surface, and it did so at whatever velocity a spacecraft achieves when it has no braking system at all. Mars 3 followed a few days later. It made it through the atmosphere. It deployed its parachute. It fired its retro-rockets. It touched down. And it transmitted data for exactly 20 seconds before going permanently silent, leaving behind a single blurred image that showed nothing identifiable. Gray background with no discernible detail. 20 seconds. After years of design, construction, testing, launch, and a journey of nearly 500 million kilometers, 20 seconds of data. The cause was probably the dust storm. Static electricity generated by the swirling particles may have disrupted the electronics, though researchers still debate this, and the uncertainty itself is instructive. On Mars, even the failures can be mysterious. The United States landed its first successful missions on Mars in 1976, when the 2 Viking landers touched down in Chrysa Planitia and Utopia, Planitia respectively. Viking 1 touched down on July 20, 1976, and Viking 2 followed on September 3, 1976. Both missions were genuine triumphs. The first successful landing on Mars came on July 20, 1976, when NASA's Viking 1 lander touched down in Chrysa Planitia. The massive 576-kilogram lander dropped from an orbiting mothership using a parachute and rocket engine, and it operated for more than 6 years, far beyond its original 90-day mission. Viking demonstrated that a soft landing on Mars was physically achievable. It demonstrated that the atmosphere, hostile as it was, could be navigated if you built the right system. It was a genuine moment of arrival. And then, for more than a decade, there was mostly silence and failure. The Soviet Phobos, one mission in 1988, was lost in transit when a routine software upload accidentally sent a command that shut off the attitude control thrusters, causing the spacecraft to lose its orientation toward the Sun and drain its batteries. Phobos 2 reached Mars orbit and was conducting a successful study of the planet and its moon when an onboard computer malfunction ended the mission, just before it was to deploy landers onto Phobos's surface. In 1992, NASA's Mars Observer failed as it approached Mars, likely due to a rupture in the bipropellant fuel pressurization system. The spacecraft, which cost approximately $813 million in total, fell silent 3 days before it was scheduled to enter Martian orbit. No signal was ever received again. Then came 1999, which deserves its own chapter in the history of human error. Not because the failures were violent or explosive, but because they were embarrassing in a way that cut directly to the heart of what makes Mars missions so unforgiving. NASA had adopted a philosophy called faster, better, cheaper under Administrator Daniel Goldin, an ethos articulated from the early 1990s onward that sought to reduce mission costs by building smaller, more focused spacecraft. In theory, this was reasonable. In practice, for Mars, it turned out to be a policy that demanded margin be removed from the very systems that had the least margin to spare. The Mars Climate Orbiter launched in December 1998, designed to study Martian weather patterns and act as a communications relay for the Mars Polar Lander. It was a 638-kilogram robotic space probe built at a cost of $125 million. It arrived at Mars in September 1999 after a 9-month journey. It entered the Martian atmosphere on a trajectory that had been gradually drifting off course for months, and it was destroyed. The investigation that followed identified one of the most remarkable single-cause catastrophic failures in the history of space exploration. The ground software that controlled the thruster firings used English units, pounds of force, while the onboard software that read those commands expected metric units, newtons. The discrepancy was small at any individual moment, but it accumulated over 9 months, and the accumulated error drove the spacecraft to enter the atmosphere at an angle that no heat shield was designed to survive. A unit conversion error, not a design failure, not a manufacturing defect, not an unforeseen physical phenomenon. A unit conversion error, the kind of mistake that would earn a student a failing grade on a physics problem set. It cost $125 million and 9 months of flight time and a mission designed to study the weather of another world. The engineering and management failures behind this are worth understanding carefully because they reveal something general about Mars missions. At least 2 engineers had noticed the discrepancy during the mission and flagged it in reports. The reports were not acted upon. The culture of the mission, the cost pressures, the schedule pressures, the optimism that the problem was not as serious as it appeared, produced an environment in which warning signs did not generate corrective action. On Mars, warning signs that do not generate corrective action generate debris. That same year, 1999, the Mars polar lander was supposed to touch down in the southern polar region of Mars, searching for water ice. It entered the atmosphere on December 3, 1999. Communication was lost. Nothing was ever heard from it again. The investigation determined, with some confidence but not certainty, that a software error in the landing leg sensors probably caused the spacecraft to think it had touched the surface when it was still approximately 40 meters in the air. The retro rockets shut off. The lander fell. It hit the surface at a speed that destroyed it utterly. 2 probe impactors called Deep Space 2 that had been attached to the polar lander for the ride to Mars were also released during descent, designed to crash into the surface and burrow in to measure water content. Neither was ever heard from again. 3 missions in 1 year. 3 failures. None of them caused by the fundamental physics of the Martian atmosphere. All of them caused by human and software error. The kind of error that, on Earth, has recovery mechanisms, has redundancies, and has the possibility of catching and correcting before the consequences become irreversible. On Mars, there is no catching and correcting. There is only the moment of failure, silent and final, arriving at the speed of light 11 minutes after the spacecraft has already ceased to exist. Here is where the causal logic of Mars landings begins to reveal its deepest structure. The atmospheric problem, the communication delay, the mass scaling problem. These are the fixed constraints. They cannot be wished away. But stacked on top of them is a second category of constraint, the organizational and human constraints that arise precisely because the fixed constraints are so severe. Because a Mars landing requires perfect autonomous execution in 7 minutes, the software that controls that execution must be correct before the spacecraft leaves Earth. There is no patching software mid-mission, no update sent on the day of landing to fix a bug that was just discovered. Whatever is wrong with the software when the spacecraft launches is wrong with it when it arrives at Mars. This means the software must be validated with extraordinary care, tested against every foreseeable scenario, checked and rechecked by teams who have been working on it for years, and who are, being human, subject to the specific failure mode of long-duration expertise. The failure mode where familiarity breeds confidence, and confidence breeds a tendency to stop questioning. Pause here, briefly. This is a pattern that will repeat. The Viking landers worked. They showed that Mars landing was possible. And in the decades between Viking and the modern era of landings, that demonstrable possibility seems to have eroded some of the institutional caution that Viking's development required. You can land on Mars. It has been done. You can build a landing system. It has been done. The problem is known. The solutions are known. This institutional memory of prior success, disconnected from the specific difficulty of each new attempt, is one of the subtler threats that Mars exploration carries. NASA is not unique in this. The European Space Agency lost its first Mars lander, Beagle 2, on Christmas Day 2003. Beagle 2 was a British-built probe carried aboard the Mars Express orbiter. It separated from its carrier spacecraft on December 19, 2003, and was never heard from again. For over a decade, its fate was unknown. Then, in 2015, researchers examining orbital imagery from NASA's Mars Reconnaissance Orbiter found it, not as a crater, not as scattered debris, but sitting on the Martian surface, apparently intact. Beagle 2 had survived the landing. Its heat shield had performed. Its parachute had deployed. It had descended through the atmosphere and touched down in one piece on Isidis Planitia, roughly 2 degrees north of the equator. But at least 2 of its 4 solar panel petals had not unfolded correctly. The sequence required all 4 panels to deploy before the radio antenna could be accessed. A design choice that, in retrospect, created a single point of failure that a partial success could not overcome. Beagle 2 was, extraordinarily, tantalizingly close to success, while still completely failing its mission objective. It had survived the hardest part. It died in the easiest part. And for 11 years, nobody knew. ESA's second attempt at landing on Mars came in October 2016, with the Schiaparelli lander. Schiaparelli was officially a test vehicle. Its primary purpose was to demonstrate EDL technologies for future missions, not to conduct extended surface science. This meant that losing it would not destroy a major scientific return. It also meant that the mission was under intense scrutiny, because the point of a demonstration is to learn, and what it demonstrated in the end was a failure mode so specific and so consequential that it became a case study in the fundamental problem of autonomous systems operating in unpredictable environments. Schiaparelli entered the Martian atmosphere on October 19, 2016, transmitting data in real time to the trace gas orbiter flying overhead. The atmospheric entry occurred normally. The parachute deployed at an altitude of 12 kilometers, traveling at approximately 1,730 kilometers per hour. The heat shield was released at 7.8 kilometers. Everything was proceeding according to plan. Then, as the spacecraft oscillated on its parachute tether, it was subjected for about 1 second to a violent rotation that was outside the design specifications of its inertial measurement unit, the sensor that tracked the vehicle's rotational rate during descent. The IMU became saturated, meaning it had exceeded its maximum measurable value and was no longer returning valid data. This saturation event lasted only about 1 second. That 1 second of bad sensor data was merged into the navigation system and generated an estimated altitude that was negative, that is, below ground level. The guidance computer, reading that it was already on the surface, triggered its landing sequence. It jettisoned the parachute, fired its braking thrusters for 3 seconds instead of the planned 30, and activated its surface systems. In reality, the vehicle was still at an altitude of approximately 3.7 kilometers. It entered free fall. It struck the surface at an estimated speed of several hundred kilometers per hour. Investigations suggest approximately 300 to 540 kilometers per hour, destroying the lander on impact. The fuel tanks may have ruptured on impact. The crater left in Meridiani Planum was visible from orbit. 1 second of sensor saturation. A 1-second mechanical event, the lander swinging on its parachute tether more violently than expected, produced a chain of autonomous decisions that ended the mission in under a minute. The investigation that followed identified that the IMU was not malfunctioning. It was working correctly. It simply could not measure spin rates above its design maximum, and no provision had been made for what the software should do when the sensor hit its limit. The system was designed for expected conditions. The expected conditions were not the actual conditions. This is the deeper lesson that Schiaparelli teaches, and it echoes through every Mars landing failure. Mars has a persistent tendency to produce conditions that are outside the expected range. The atmosphere is not perfectly predictable. Dust storms change its density. Solar heating creates thermal variations. Local topography generates turbulence. The exact conditions a spacecraft will encounter during those 7 minutes are, despite decades of atmospheric modeling and satellite observation, not fully knowable in advance. Atmospheric variability across a Martian year limits the ability to develop a single common EDL system, and significant atmospheric dust content, a random occurrence, increases the temperature of the lower atmosphere, reducing density and requiring conservatism in the selection of landing site elevation. That unpredictability is not a problem that better sensors alone can solve. It is a fundamental property of a dynamic atmosphere on a dynamic planet. The models improve with every mission. The data sets grow. The predictions get better. And the planet still manages, with some regularity, to do something unexpected. Consider the broader pattern. Mars 2, incorrect entry angle, parachute failure, impact. Mars 3, touchdown, then 20 seconds of silence. Mars polar. Lander, leg sensors trigger premature engine shutdown, fall and impact. Beagle 2, landing survived, solar panel failure. Schiaparelli. 1 second of sensor saturation triggers a cascade of autonomous errors. Impact. The causes are different in each case. The mechanism is different. The system that failed is different. But the underlying structure is the same. A complex autonomous system operating in a partially unpredictable environment under the absolute constraint that no human can intervene reaches a moment where one input is wrong, and the wrongness propagates through the system faster than any safeguard can catch it. Now turn from failure to success, because the successes are equally instructive, and they are more remarkable than they are usually given credit for being. The Viking landings of 1976 were the result of a program that began in earnest in 1968 and cost, in total, roughly $1 billion in 1970s money. The landing system was exhaustively tested. The team spent years conducting test entries in wind tunnels, simulating Martian atmospheric conditions with the best data available at the time from Mariner 4 and Mariner 9 flybys. The parachute system was tested at altitudes and speeds designed to approximate Martian conditions as closely as Earth's atmosphere permitted. The terminal descent rockets were fired thousands of times. The landing legs were tested for every foreseeable surface topology. And when Viking 1 touched down on July 20th, 1976, the system performed almost exactly as designed, because the designers had made the design extraordinarily conservative, with margins built in at every stage, and because they had started from the assumption that Mars would surprise them and had tried to anticipate as many surprises as possible. Viking succeeded also because it was relatively light. At 576 kilograms, The lander was well within the capability of the parachute system to decelerate to a useful speed before the retro rockets needed to take over. The atmospheric double bind, too thin for parachutes to work well, too thick to ignore, was a real constraint, but it was a manageable one at Viking's mass. The parachutes, 67 feet in diameter, could deploy at supersonic velocity and still generate enough drag to pull the spacecraft from 250 meters per second down to a speed where the retro rockets could take it the rest of the way. The lesson of Viking is not simply that careful engineering works. It is that careful engineering at a manageable mass works. Every Mars mission since Viking has had to wrestle with a creeping problem. Science demands more capability, more instruments, larger rovers, more sophisticated hardware, and all of that additional capability requires additional mass. The atmosphere that handled Viking's 576 kilograms began to strain as masses crept upward. By the time Curiosity was being designed, the traditional toolkit of parachutes and retro rockets was genuinely insufficient. Something new was required. That something new, the sky crane, was conceived in the early 2000s by a team at NASA's Jet Propulsion Laboratory in Pasadena, California, led by an engineer named Adam Stelzner. The sky crane system combined a protective aeroshell with supersonic parachutes and a rocket-powered descent stage, and was developed under Stelzner's leadership. It was an 8-rocket jetpack that would hover above the surface, lower the rover on cables to a soft touchdown, and then fly itself away to crash at a safe distance. It was precisely the kind of engineering solution that sounds, when described, like something a child might invent, and which turns out, on close examination, to be the result of extremely serious thought about an extremely serious problem. When Stelzner presented the sky crane concept to NASA management, the reaction was mixed at best. The skepticism from NASA leadership was understandable. Stelzner himself acknowledged that the design looks a little bit crazy, though he insisted it was the least crazy of the methods you could use to land a rover the size of Curiosity on Mars. There was no way on Earth to test how the rocket-powered sky crane would perform on Mars. Engineers could run simulations and verify their calculations repeatedly, but they could never know for certain that Curiosity would actually survive the maneuver. The Curiosity rover, launching in 2011, weighed approximately 900 kilograms, too heavy for airbags, too heavy for the parachute plus retro rocket approach that had worked for smaller landers. The sky crane was not chosen because it was elegant. It was chosen because nothing else worked at that mass. And on August 5th, 2012, the sky crane worked. Curiosity touched down on the floor of Gale Crater, a wide basin just south of the Martian equator, at near vertical velocity of about 0.75 meters per second and minimal tilt. The entire EDL sequence, from atmospheric entry to landing, had gone through 6 distinct vehicle configurations and fired 76 pyrotechnic devices without a single failure. The EDL phase for Curiosity began when the spacecraft reached the top of the Martian atmosphere, traveling at about 13,200 miles per hour. The parachute, almost 16 meters in diameter, deployed about 254 seconds after entry, at an altitude of about 11 kilometers. 24 seconds later, the heat shields separated. The sky crane's 8 variable thrust rocket thrusters slowed the descent stage until it was hovering, and then lowered the rover on cables to the surface at about 0.75 meters per second, roughly the pace of a brisk walking stride. Upon the touchdown, pyrotechnic cutters severed the cables, and the descent stage flew itself away to crash 650 meters from the rover. JPL engineers monitoring the telemetry in real time 7 minutes after the events had already concluded, received confirmation that Curiosity had landed. The response inside the mission control room in Pasadena became one of the most widely shared moments in recent space exploration history. Scientists and engineers who had spent years working on the problem, who understood exactly what could have gone wrong and hadn't, burst into tears and embraced each other. It was not a simple relief. It was something more specific. The release of the knowledge that an enormous, sustained act of technical will had succeeded against odds that everyone in the room understood precisely. This is worth pausing on. The celebration at JPL after Curiosity's landing was not the uncomplicated joy of a team that had never doubted their own success. It was the celebration of people who knew exactly what they had attempted, who had spent years imagining the specific ways it could fail, and who understood, at the moment of confirmation, that this time, all of the things that could have gone wrong had not gone wrong. The distinction matters. The 7 minutes of terror are not theatre. They are the lived experience of engineers who know the probability space they are operating in. Perseverance landed on February 18, 2021, using an updated version of the same sky crane system, with one significant addition, the Lander Vision System, which used terrain relative navigation to allow the spacecraft to identify safe landing spots in real time during descent, comparing camera images of the surface to onboard maps and steering away from hazards. This capability, landing on a specific safe spot rather than accepting whatever surface happened to be within a broad landing ellipse, represented a genuine step forward. Perseverance touched down in Jezero Crater, a former lakebed chosen for its potential to preserve evidence of ancient microbial life, with precision that would have seemed impossible to the Viking-era engineers. The sky crane that delivered Curiosity was adapted for the Perseverance rover, which weighed 1,025 kilograms, heavier than its predecessor. Each incremental mass increase demands a recalibration of the entire EDL sequence: the parachute opening altitude, the thruster burn duration, the descent rate, the cable length, because none of these parameters scales linearly with mass in the Martian atmosphere. China's Tianwen-1 mission successfully landed its Zhurong rover on the Utopia Planitia Plains in May 2021, making China only the second nation to successfully operate a rover on Mars. This was a remarkable achievement, accomplished on the first Chinese attempt to land on Mars, and it represented a genuine diversification of the global Mars exploration enterprise. Some researchers attribute the success partly to the benefit of learning from decades of NASA documentation and published research on EDL engineering, supplemented by China's own significant investment in atmospheric modeling. Others note that Tianwen-1 also made a strategic choice to first enter Martian orbit and spend several months observing its landing site before committing to descent, a cautious approach that Viking-era engineers would have recognized as wise. Take stock of where we are. We have traced the broad historical arc of Mars landings from 1960 to 2021. We have established the two fixed physical constraints, the atmospheric double bind and the communication delay, that define every landing attempt regardless of era or nationality. We have seen how human and organizational failures layer on top of those physical constraints to produce additional loss mechanisms. And we have seen how the engineering community has responded to escalating payload masses with increasingly elaborate landing systems, from simple retro rockets to airbags to the sky crane. Each new system more complex, requiring more things to go right, generating more potential failure modes, even as it solves the immediate problem. What we have not yet done is descend, in detail, into the specific layers of the problem, the physical, the mechanical, the navigational, the thermal, to understand what is actually happening during those 7 minutes. That is where the story becomes most specific, most technically rich, and, in a certain sense, most awe-inspiring. Because when you examine the 7 minutes closely, when you trace what the spacecraft actually experiences in sequence, from the moment it touches the outer wisps of the Martian atmosphere to the moment it comes to rest on the surface, you discover that the engineering problem is not one problem. It is a cascade, a linked chain in which each phase depends on the previous phase having succeeded, where no phase offers a chance to pause and reassess, and where the atmosphere itself, variable, dusty, imperfectly modeled, is the medium through which every decision must be executed. The 7 minutes begin before most people think they begin. A spacecraft approaching Mars has been traveling for somewhere between 6 and 9 months, depending on the trajectory chosen for that particular launch window. It has crossed several 100 million kilometers of interplanetary space, guided by occasional thruster firings calculated by navigators on Earth, who track its position, using radio signals measured to extraordinary precision. By the time it approaches Mars, the spacecraft knows where it is to within a few kilometers, which sounds impressive until you remember that a few kilometers of uncertainty, translated into an entry angle, can mean the difference between a survivable trajectory and one that ends in the atmosphere. The entry angle is the first of the cascade's links, and it is one of the most demanding. A spacecraft entering the Martian atmosphere must do so at an angle within a window that is, depending on the mission, somewhere between 1 and 3 degrees wide. Too shallow, and the vehicle skips off the atmosphere like a stone skipping off water, bouncing back into space on a trajectory that cannot be corrected. Too steep, and the vehicle enters at a sharper angle, generating more heat per unit time, creating a thermal load that overwhelms the heat shield before the deceleration is complete. Mars 2, in 1971, entered too steeply, and its parachute sequence never had the chance to begin. 1 to 3 degrees. On a sphere 6,800 kilometers in diameter, approaching from hundreds of millions of kilometers away, hitting a target angular window of 1 to 3 degrees requires navigation of a precision that would have seemed implausible to engineers of any previous era. It is achieved through a combination of deep space tracking networks, the NASA. Deep Space Network operates dish antennas at Goldstone in California's Mojave Desert, near Madrid in Spain, and near Canberra in Australia. And trajectory correction maneuvers, small thruster firings executed weeks or months before arrival, that nudge the spacecraft onto the correct approach path. By the time the spacecraft is a week from Mars, it is, in navigational terms, committed. The final trajectory correction maneuver happens days before arrival. After that, the entry angle is essentially fixed. The aeroshell that contains the spacecraft during entry is the first active system to earn its mass. It is a blunt body, typically a 70-degree sphere cone shape, a design inherited from the Viking era that has survived largely unchanged because it happens to produce an optimal balance of drag coefficient and thermal load distribution. The bluntness is counterintuitive. You might expect that a pointed nose would cut through the atmosphere more cleanly. But in hypersonic flow, a pointed nose concentrates heat at a single point. A blunt body creates a detached bow shock, a compressed region of heated gas that stands off the vehicle's surface, shielding it. The heat goes into the gas, not the spacecraft. The aeroshell is the reason the spacecraft can survive the entry phase at all. Peak heating during entry typically lasts for a period of about 2 minutes, during which the outer surface of the aeroshell reaches temperatures of roughly 1,600 degrees Celsius. The heat shield material, a substance called pica, phenolic impregnated carbon ablator, developed at NASA's Ames Research Center in Mountain View, California, works by ablating. It burns away in a controlled fashion, carrying the heat with it as gas rather than letting it conduct inward to the spacecraft. The engineer's term for this is ablative cooling. The everyday term might be, the heat shield eats itself to save the vehicle. As the heat shield material gasifies and streams backward in the hypersonic flow, it forms a protective layer between the superheated shock layer gas and the underlying structure. If the ablation proceeds correctly, the spacecraft inside the aeroshell remains within survivable temperature limits. If the aeroshell has any flaw, any gap, any seam, any manufacturing imperfection that allows hot gas to penetrate, the vehicle can be destroyed within seconds. At the same time that the heat shield is absorbing its peak thermal load, the vehicle is experiencing its peak deceleration. The forces can reach 10 to 15 times the acceleration of gravity, 10 to 15 Gs, for a brief period. Every component of the spacecraft must be able to survive this deceleration without any structural failure, without any electrical connection shaking loose, without any mechanism jamming. These forces are tested on Earth using centrifuges and vibration tables. But there is an irreducible gap between simulated forces and actual aerodynamic forces in a real hypersonic flow. Some researchers have noted that this gap is not well characterized, and that the entry phase remains, in certain respects, the least testable portion of the entire landing sequence. Now, there is something here that most descriptions of Mars landings pass over quickly, and it deserves more attention. The entry phase does not proceed identically every time, even for missions using identical hardware. The Martian atmosphere, through which the aeroshell is descending at hypersonic velocity, varies. It varies with latitude. It varies with season. It varies with time of day. It varies with the presence or absence of regional or global dust storms. Atmospheric density variations from 8 to 30 kilometers altitude can significantly affect when and how the heat shield performs. Dust storms, which can begin locally and expand to cover the entire planet within weeks, heat the lower atmosphere and reduce its density, changing the aerodynamic properties of the descent corridor in ways that are partially predictable from orbit, but never fully certain. The Mariner 9 mission, arriving in 1971, found a global dust storm already in progress when it reached Mars. The storm lasted for months. Had Mariner 9 been a lander rather than an orbiter, the atmospheric density changes caused by that storm, which can reduce lower atmosphere density by 10 to 20% during severe events, could have meant that a parachute designed to deploy at a specific speed and altitude would have opened at the wrong point in the descent. The engineers would not have known in advance. The spacecraft would not have been able to adapt. The planet, in that sense, was simply not what the models said it would be on that particular day. This variability is a constraint that sits above all engineering. You can improve your models. You can increase the number of orbiting atmospheric sensors. You can study the dust cycle and try to predict when storms will develop. But the Martian dust cycle remains, as of the present day, only partially understood. Researchers at the Ames Research Center and at the International Mars Research Center at the University of Arizona have spent decades developing models of Martian dust transport. How dust gets lifted by surface winds, how it interacts with solar radiation, how regional storms merge and intensify. Some researchers believe the dust cycle is fundamentally chaotic, that small perturbations in surface conditions can cascade into dramatically different atmospheric outcomes in ways that no model can capture at useful timescales. Others believe that with enough data and computational power, the dust cycle can be predicted weeks in advance with acceptable accuracy. The truth, as of today, lies somewhere between these positions. We do not fully know which view is correct, and that uncertainty is not merely academic. It has operational consequences for every future lander. The aeroshell's job lasts until the spacecraft has decelerated from entry velocity down to roughly Mach 1.5 to 2. Still supersonic, but slow enough that a parachute can deploy without destroying itself. This transition takes roughly 3 to 4 minutes. At that point, the spacecraft is typically at an altitude of somewhere between 7 and 15 kilometers, depending on the mission architecture, and it is still falling fast enough to be lethal if it hits the surface. The parachute must now arrest this descent to a speed at which the final powered landing system can take over. Parachutes on Mars are not the same as parachutes on Earth, and the difference is not simply one of scale. A parachute generates drag by pushing against the air through which it moves. On Earth, at relatively low velocities and in a dense atmosphere, a moderate-sized parachute can decelerate a human or a payload quickly and effectively. On Mars, the atmosphere is so thin that to generate equivalent drag force, you need either a much larger parachute or a much higher velocity, or both. The parachutes used on Mars missions are disc gap band parachutes, a design specifically developed for supersonic deployment in thin atmospheres, and they must open at speeds that would destroy a conventional parachute on Earth. They are deployed by mortar, literally fired from the spacecraft using a small explosive charge that yanks the parachute out into the airflow at high speed. Because at Mach 1.5, the atmospheric forces are insufficient to pull a conventionally deployed parachute into the flow fast enough to be useful. The disc gap band design has a specific geometry: a solid disc at the top, a gap in the middle that allows some flow through, and a band at the bottom. The gap and band combination reduces oscillation during deployment and stabilizes the parachute at supersonic velocities, preventing it from collapsing or violently swinging the payload beneath it. Even so, the opening shock, the sudden jolt as the parachute fills with air, is a significant mechanical event that subjects both the canopy and its attachment points to extreme loads. The Perseverance parachute, which was roughly 21 meters in diameter, opened at approximately Mach 1.7 and was subjected to an opening load of several metric tons. Here is where the atmospheric double bind reasserts itself in its most concrete form. The parachute on Mars must be large enough to generate sufficient drag in the thin atmosphere, but the thin atmosphere also means it is still moving too fast when it reaches altitudes where the powered descent system must take over. On Earth, a parachute can slow a payload to a gentle enough speed that retro rockets need only the smallest additional nudge. On Mars, when the parachute has done everything it can do, when it has reached its minimum effective speed in the available atmosphere, the spacecraft is still falling at somewhere between 50 and 100 meters per second. That is between 180 and 360 kilometers per hour. At that speed, without additional braking, touchdown is fatal. The powered descent phase, retro rockets, the sky crane, whatever terminal braking system the specific mission employs, must therefore carry a much larger share of the deceleration burden on Mars than on Earth. This means more propellant. More propellant means more mass. More mass means the parachute needs to be larger to slow the heavier vehicle. A larger parachute generates more opening shock. More opening shock requires stronger attachment points. Stronger attachment points require additional mass. The mass scaling problem spirals back on itself, adding complexity at each turn. Consider this with some specificity. The descent stage of the sky crane system that landed Curiosity carried enough hydrazine propellant to fire 8 rocket engines for the duration of the powered descent phase. Those engines, the Mars landing engines, were throttleable, meaning they could vary their thrust to precisely control the descent rate. The entire descent stage, propellant included, was a significant fraction of the total launch mass. Once the rover was on the ground and the cables were cut, the descent stage flew itself away and crashed. It was not reusable. It was not recoverable. It was a one-use device, elaborate and expensive, manufactured to extraordinary precision, used for approximately a minute and a half, and then destroyed. Now think about the operational environment in which this device had to perform. It was operating at altitudes of less than 2 kilometers in an atmosphere where wind speeds can reach hundreds of kilometers per hour during dust storms, and where even on calm days, turbulence generated by surface heating can cause unexpected attitude variations in a hovering vehicle. The 8 engines had to precisely balance their thrust to keep the descent stage level while lowering the rover. If one engine failed, if a single thruster valve stuck, if a fuel line blocked, if a sensor gave a wrong reading, the descent stage could tilt, and a tilting descent stage would drag the rover sideways as it lowered, potentially causing a lateral velocity at touchdown that would damage or overturn the rover. The engineering response to this is redundancy. Build systems that can survive the failure of individual components. The Sky Crane had redundant sensors, redundant communications pathways, redundant pyrotechnic systems for the cable cutters. But redundancy has limits. Redundancy adds mass. At some point, the redundancy required to make a system sufficiently reliable itself becomes a mass penalty that undermines the feasibility of the mission. This tension between redundancy and mass is one of the fundamental engineering dilemmas of Mars EDL, and it has no clean resolution. Anaphora is the mind's natural rhythm in the face of cascading complexity. One thing can fail, one sensor can lie, one valve can stick, one measurement can saturate, and any one of those single failures at the wrong moment in the 7-minute sequence can end the mission that took a decade to build. The question of where in the descent chain failures are most likely to occur has been studied extensively. Robert Braun, an aerospace engineer who in 2006 published with JPL's Robert Manning what became one of the foundational papers on Mars EDL challenges while at the Georgia Institute of Technology, identified several categories of risk that persist across mission architectures: atmospheric variability and density uncertainty, parachute deployment dynamics, terminal descent system performance, landing site hazard avoidance, and the fundamental limitation that all successful landings to date had been confined to low elevation sites. Braun's 2007 paper with Richard Manning, titled Mars Exploration Entry, Descent and Landing Challenges, remains one of the most cited references in the field. It identified that fully half of the surface of Mars had been out of reach of past landers due to insufficient atmosphere for deceleration, that the higher elevations of the planet, precisely the regions that are often most scientifically interesting because they expose older geological layers, are essentially inaccessible with existing EDL technologies. This elevation constraint is subtle but profound. It is not simply that higher terrain is harder to reach. It is that the atmosphere, already too thin, becomes even thinner at altitude. High regions on Mars, and Mars has some extraordinarily high regions, including the volcanic plateau of Tharsis, which rises several kilometers above the mean surface level, have so little atmosphere above them that a parachute deploying at any reasonable altitude would find barely enough resistance to generate meaningful drag. At some elevations, the parachute simply cannot do enough work. The vehicle arrives at the terminal descent altitude, still traveling too fast for the retro rockets to handle. There is no answer to this with existing technology. Those parts of Mars are, for now, unreachable by landers. It is worth naming a specific location here. Olympus Mons, the largest volcano in the solar system, rises approximately 22 kilometers above the mean Martian surface. Its summit plateau sits at an elevation where the atmospheric pressure is roughly 30 to 40 pascals, compared to about 600 pascals at the mean surface level. A lander attempting to reach the summit of Olympus Mons would need to operate in an atmosphere that is, at that altitude, essentially a near vacuum. No parachute-based EDL system can function there. No current retro-rocket system could carry enough propellant to slow a vehicle from entry velocity to rest at that altitude. Olympus Mons will remain unvisited for the foreseeable future, not because humans lack the ambition to reach it, but because the laws of fluid dynamics are not negotiable. Among the regions that are accessible, landing site selection has become one of the most scientifically charged debates in planetary exploration. Scientists want to land in geologically interesting places, crater floors that might preserve biosignatures, ancient lakebeds, valley systems carved by water billions of years ago. Engineers want to land in places that are flat, low in elevation, relatively dust-free, and clear of large boulders. These preferences are often in direct conflict. The selection of Gale Crater for Curiosity was a compromise that required new landing technology, the terrain-relative navigation that Curiosity could not use, but that Perseverance subsequently employed, to make the scientific target accessible within engineering constraints. The Jezero crater landing, where Perseverance touched down in February 2021, was considered by many EDL engineers to be at the outer limit of what was possible given the available technology. Jezero's floor is geologically rich, an ancient river delta, a former lake bottom, exactly the kind of site where evidence of past life might be preserved in layered sedimentary rock. It is also crossed by rock formations, ridges, and surface irregularities that made the landing hazardous by any previous standard. The Lander Vision System, a camera and terrain matching algorithm that allowed Perseverance to identify hazards during descent and steer away from them, made the landing possible. Without it, Perseverance could not have safely targeted Jezero. But even the Lander Vision System is not perfect, and it is not magic. It works by comparing camera images of the surface, taken during descent, against preloaded maps of the landing area built from orbital data. If the orbital maps are inaccurate, if a boulder has been deposited by a recent impact, if a dust deposit has changed the apparent texture of the surface, the system may not correctly identify hazards. It is a genuine improvement over purely ballistic landing approaches, but it is an improvement operating within the same fundamental constraint space. Imperfect information, autonomous execution, no second chances. The terminal phase of descent, the final moments before touchdown, is perhaps the most mechanically delicate. For a sky crane landing, the rover is being lowered on cables at approximately 0.75 meters per second, equivalent to a brisk walking speed, while the descent stage hovers above, fighting to maintain level flight in whatever wind conditions exist at the surface. The rover's wheels and suspension systems serve as the landing gear. They flex on contact to absorb the residual vertical velocity. The moment of touchdown must be detected precisely by sensors in the landing legs, because the cable-cutting pyrotechnics must fire within seconds of the wheels touching the ground. If the touchdown detection fails, if the system thinks the rover has landed when it hasn't, or thinks it hasn't when it has, the cable-cutting sequence runs at the wrong time, with consequences that range from a tilted rover to a destroyed one. After the cables are cut, the descent stage must fly itself away to a crash site that is far enough from the rover to avoid damaging it with debris, but close enough that it can reach that site before running out of propellant. This seems like a minor detail, but it is a real engineering challenge. A rocket-powered vehicle that is no longer constrained to hover. Precisely must execute a brief controlled flight across an unfamiliar surface to an impact point calculated during the mission design phase, based on wind conditions that may not match actuals in an atmosphere that is doing whatever the atmosphere does on that particular sol. An anaphora of fragility. The cable cutter must fire. The cables must sever cleanly. The descent stage must detect the separation and begin its divert maneuver. The divert maneuver must produce enough lateral velocity to clear the rover's vicinity before propellant runs out. Each of these events must succeed. None of them can fail. That chain of dependency, that long, unbroken string of must-work systems operating autonomously in a foreign environment, is the defining character of a Mars landing. It does not become less true as the engineering improves. It becomes, if anything, truer. Each new system added to solve a previous problem extends the chain. Each new sensor introduced to reduce uncertainty adds a component that can malfunction. Each new algorithm written to handle edge cases contains code that may contain edge cases of its own. Rob Manning, another JPL engineer who has led or contributed to EDL for Pathfinder, the Mars exploration rovers, Curiosity, and other missions, has written and spoken extensively about this fundamental tension. Manning, whose work spans nearly 4 decades of Mars EDL development, has described the problem in terms that any engineer will recognize. The goal of landing on Mars is not to build a perfect system, because a perfect system is not achievable. The goal is to build a system whose failure modes are known, whose single-point failures have been eliminated to the greatest extent possible, and whose probability distribution of outcomes is sufficiently weighted towards success that the mission is worth attempting. This is a profound reframing. It means that every Mars landing team is not claiming that their vehicle will definitely land. They are claiming that, to the best of their knowledge, the probability of failure is acceptably low. The distinction is not semantic. It is the lived reality of Mars EDL engineering. And that probability assessment is itself uncertain. It is based on models of the atmosphere that may be wrong in ways not yet discovered. It is based on test data gathered on Earth in conditions that can only approximate Mars. It is based on the performance history of previous missions, which provides a data set that is, given the total number of Mars landing attempts, statistically thin. You cannot derive a robust probability distribution from a dozen successful landings and a dozen failures, especially when each mission uses different technology, different mass, different landing site, different atmospheric season. The historical record is informative, but it is not a controlled experiment. This is the point at which the engineering honesty of the people who actually do this work becomes most apparent and most worth appreciating. When JPL or ESA or CNSA publishes a probability of landing success for a given mission, that number is not a guarantee. It is not even a firm estimate in the sense that most people understand estimates. It is an expression of the team's best current understanding of a problem that remains, at its physical core, incompletely characterized. The universe, as Feynman once said, is not interested in whether its behavior is convenient for us to measure. Stand on the surface of Mars for a moment, not at the edge of a crater, not on the flanks of Olympus Mons, but in the middle of Jezero Crater's ancient river delta, the place where perseverance sits right now as these words reach you. The ground beneath your feet is rust-red and finely grained, mixed with angular stones of basalt and olivine. The sky above is not black. It is a pale, dusty butterscotch, tinted pink by the particulate that hangs perpetually in the thin air. The sun is visible, but smaller than it looks from Earth, about 2/3 the angular diameter, casting a cold, clear light that produces shadows with unusually sharp edges because there is so little air to scatter it. The wind is blowing softly most days, occasionally rising to produce sustained gusts that carry enough fine dust to coat every surface within hours. The temperature at the surface, on a summer afternoon near the equator, might reach a few degrees Celsius. Within an hour of sunset, it will fall to -70. Stand there and look up. Somewhere above you, invisible, a spacecraft is falling. It has been falling for 6 months. It entered the thin outer wisps of this atmosphere 3 minutes ago. In 4 minutes, it will either be sitting on the ground near you, or it will be debris spread across a swath of red plain. From where you stand, you will hear nothing. The parachute deployment, if it works, is subsonic by the time the sound reaches the ground, and by then it will have dissipated entirely. The retro-rocket burn, if it works, generates a whisper of thrust in an atmosphere too thin to carry the roar you might expect. The touchdown itself produces a small impact that vibrates the ground for a fraction of a second. That silence is, in a way, the most honest representation of what a Mars landing actually is. It is an event that happens without witnesses, without ceremony, in a place that humanity has not yet reached in person. The engineers who built the vehicle are 200 million kilometers away, watching telemetry signals on computer screens, waiting for confirmation that will arrive 11 minutes after the fact. The planet does not care. The atmosphere does what it does, and the spacecraft falling through it either executes its sequence correctly or does not. Now step back from that image and return to engineering. Because within the 7 minutes that separate atmospheric entry from landing, there are several distinct phases, each with its own physics, its own failure modes, and its own relationship to the atmospheric double bind. We have traced the entry phase and the parachute phase in broad outline. Now the detail becomes finer, and the complexity becomes more layered, and the ingenuity of what humans have actually achieved becomes more apparent. The moment of heat shield separation is one of the most critical transitions in the entire EDL sequence. The heat shield is jettisoned after peak heating is over, and the vehicle has decelerated to a speed where the aerodynamic heating is no longer dangerous. For Perseverance, the heat shield separated at an altitude of approximately 8 kilometers, traveling at roughly 400 meters per second. The jettison is pyrotechnic. Small explosive bolts fire, severing the structural connections, and the heat shield falls away and is abandoned on the Martian surface below. The moment the heat shield separates, the spacecraft's sensors can see the ground for the first time. Radar altimeters fire and begin measuring the distance to the surface. For the lander vision system, cameras begin capturing images of the terrain below and comparing them to the preloaded maps. This is the first moment in the descent when the spacecraft can actually know, in real time, where it is relative to the surface. Before heat shield separation, it is flying blind with respect to the terrain, entirely dependent on pre-calculated trajectories and inertial measurements that may have accumulated small errors over the preceding minutes of hypersonic flight. The radar data and the terrain navigation data must be fused correctly by the onboard computer. They carry different information. The radar measures vertical distance to the surface with high accuracy, but cannot identify specific features. The terrain camera identifies specific features, but may have geometric distortion due to vehicle attitude and altitude uncertainty. The The fusion algorithm must weight these two sources appropriately and produce an estimate of the vehicle's state. Its position, velocity, and orientation that is accurate enough to guide the terminal descent to the chosen landing spot. This is where the Schiaparelli failure, described earlier, becomes most instructively relevant. In Schiaparelli's case, the fusion algorithm was receiving corrupted data from the IMU, the inertial measurement unit, and was weighting it incorrectly. The radar was telling the truth. The altitude was positive, meaning the spacecraft was above the ground. The IMU was lying. It had saturated during a brief violent rotation and was reporting a rotational rate that, when integrated into the navigation solution, produced a negative altitude. The fusion algorithm chose to believe the IMU over the radar. It was programmed to do so. The consequence was fatal. The lesson that ESA and other agencies drew from Schiaparelli was not simply to redesign the IMU or to change the saturation threshold. The deeper lesson was about the architecture of sensor fusion. When two sensors disagree, the system needs a principled way to determine which one to trust, and that determination must account for the possibility that one sensor may have entered a failure mode that is, within its own framework, internally consistent. An IMU that has saturated and is then reporting zero rotation is not reporting random noise. It is reporting a coherent, plausible signal. The problem is that the signal is wrong. Distinguishing coherent but wrong signals from correct signals is one of the hardest problems in autonomous systems engineering, and it is hardest precisely when the system is operating in conditions that push sensors toward their design limits. The Martian atmosphere pushes sensors toward their design limits. That is not a coincidence or an oversight. It is a consequence of the atmospheric double bind. Because the atmosphere is both thin and active, thin enough to make parachute dynamics unpredictable, active enough to generate turbulence and oscillation in descending vehicles, the mechanical environment during EDL is inherently more extreme than Earth analog tests suggest. Parachutes generate oscillation as they fill. Vehicles swing on their risers. The combination of supersonic deployment, thin air dynamics, and unavoidable structural flexibility produces a descent environment where sensors are working at or near their limits, and where unexpected events, a slightly more energetic parachute fill, a slightly stronger crosswind, a surface heating anomaly that produces a localized updraft, can push sensors past those limits. The engineering response is to design sensors with margins above the expected maximum environment. Add 20% to the maximum expected rotational rate and build an IMU that saturates at that higher level. But here is the fundamental difficulty. The expected maximum environment is itself derived from models that are imperfect. The actual maximum environment on any given landing day may exceed the modeled maximum by an unknown amount. Margins built against an imperfectly known environment do not provide the same assurance as margins built against a precisely known environment. This is not a counsel of despair. It is an acknowledgement of an irreducible uncertainty that careful engineering must navigate without being able to eliminate. Consider the dust. The role of dust in Mars EDL is underappreciated in popular accounts of the problem, which tend to focus on the atmosphere's thinness to the exclusion of the atmosphere's texture. The Martian atmosphere is not simply thin. It is thin and full of particles, micron-sized grains of iron oxide and silicate, suspended by electrostatic forces and surface winds, redistributed by regional and global storms, settling on surfaces over months and years and being lifted again by the next wind event. This dust affects EDL in several distinct ways. Aerodynamically, suspended dust changes the atmosphere's effective optical properties, and contributes to solar heating of the lower atmosphere. During a major dust storm, the lower atmosphere absorbs more solar radiation, heats up, and expands upward. The result is that the atmosphere at any given altitude becomes slightly less dense during a storm. Density decreases by 10 to 20% in severe events. For a spacecraft whose parachute was sized for the nominal, non-storm atmosphere, a reduction in density at deployment altitude means less drag than designed, which means a higher velocity at the altitude where the terminal descent system must take over. That higher velocity demands more propellant from the retro rockets. If the propellant budget was calculated for nominal conditions, the vehicle arrives at the terminal descent phase with insufficient margin. This is not hypothetical. The Opportunity rover mission, which landed on Meridiani Planum in January 2004, chose an airbag landing system designed for a specific range of atmospheric conditions. Opportunity was lucky. Its landing occurred during a relatively clear period. But the Spirit rover, landing 3 weeks earlier at Gusev crater, entered during conditions that were slightly less favorable, and telemetry analysis afterward showed that the vehicle was descending faster than predicted during the final airbag cushioned bounce. The margins were there. The rover survived. But the margins were smaller than designed, and smaller margins mean a closer approach to the failure boundary. Thermally, the dust creates a different challenge during entry. Fine particles suspended at high altitude scatter and absorb infrared radiation differently than a clean atmosphere, affecting the radiative heating component of the aeroshell thermal environment. Clean atmosphere models tend to underpredict the radiative heating contribution in dusty conditions. In practice, this means that a heat shield sized for a clean atmosphere may be operating closer to its thermal limit during a dusty entry than the design analysis predicted. This is a known concern that mission teams address by building in additional thermal margin. But again, margin built against a model of uncertain accuracy provides uncertain protection. For landers that use radar altimetry during terminal descent, the dust creates a third problem. Ground-penetrating radar signals used to measure altitude can interact with the suspended dust column in ways that introduce small errors in the altitude reading, particularly if the dust density is variable at the altitudes where the radar is operating. A 1% altitude error at 200 meters translates into 2 meters of uncertainty in the touchdown position, which for a sky crane system means 2 meters of uncertainty in when to cut the cables. 2 meters at 0.75 meters per second descent velocity is approximately 2.7 seconds of timing uncertainty. In a system that must execute its cable-cutting sequence within a fraction of a second of actual touchdown, a 2.7-second uncertainty is significant. These dust-related complications compound the atmospheric variability problem in a way that makes Mars EDL more than the sum of its individual challenges. Each challenge, density variability, thermal environment uncertainty, radar interference, is manageable on its own, given sufficient margin and careful analysis. But they occur simultaneously in the same 7 minutes, acting on the same vehicle, interacting with each other in ways that are difficult to model comprehensively. The dust storm that reduces atmospheric density also changes the thermal environment. The thermal environment change affects the deceleration profile. The altered deceleration profile changes the velocity at parachute deployment. The changed deployment velocity alters the parachute dynamics. The altered parachute dynamics affect the oscillation behavior of the vehicle. The oscillation behavior of the vehicle is exactly what drove the Schiaparelli EMU to saturation. It is a chain. It is always a chain. Now there is a separate category of the problem that deserves sustained attention, because it is the one most relevant to the future of Mars exploration, and because it receives far less discussion in popular accounts than atmospheric physics and the 7 minutes of terror. That category is, what happens when you need to land something much heavier than a rover? The sky crane system that landed Curiosity and Perseverance represents the current upper bound of Mars' EDL capability for traditional mission architectures. Perseverance weighed 1,025 kilograms. The sky crane's descent stage, with its propellant, added several hundred kilograms more to the total entry mass. The aeroshell that protected everything during entry added yet more. The total mass entering the atmosphere for Perseverance was on the order of 3,600 kilograms. A human Mars mission requires landing substantially more mass. The estimates vary, depending on the architecture, the crew size, the mission duration, and the surface infrastructure needed. But the range discussed by NASA, SpaceX, and other organizations falls between 20 and 40 metric tons of landed mass, and possibly more. Some architectures propose landing the crew vehicle in one piece. Others propose pre-deploying surface infrastructure in advance and landing the crew vehicles separately. Either way, the required landed mass is 10 to 40 times greater than anything that has ever been attempted. The scaling problem at those masses becomes acute in ways that do not yield to the approaches that have worked for robotic landers. The sky crane cannot scale to 40 metric tons. The propellant mass required to perform the powered descent for that load would itself require an enormous lander, which would require more propellant, which would require a larger vehicle. The tyranny of the rocket equation applies here as mercilessly as it does everywhere in spaceflight. Parachutes that could generate enough drag to slow a 40 metric ton vehicle in the Martian atmosphere would need to be enormous, on the order of 100 meters in diameter or more, and deploying a 100-meter parachute at supersonic velocity without destroying it is an unsolved engineering problem. The two candidate approaches that have received the most serious attention are inflatable decelerators, large, lightweight structures that deploy before or after the parachute phase and increase the aerodynamic drag area without the structural weight of a rigid aeroshell, and retropropulsion, the use of rocket engines firing during the hypersonic or supersonic phase of entry to supplement atmospheric drag with direct thrust. Neither approach is proven for the mass scales required. Both have been studied extensively and have undergone limited flight testing. NASA's Low-Density Supersonic Decelerator program, conducted between 2012 and 2015, tested inflatable decelerator concepts called Supersonic Inflatable Aerodynamic Decelerators, or SIADs, at Earth analog Mars altitudes and speeds above Hawaii's Pacific Missile Range facility on Kauai. Some researchers, including Ian Clark at JPL, who led portions of the LDSD program, reported partial success with the inflatable decelerators themselves, while the large diameter parachutes tested in the program showed inconsistent performance. In one test, the parachute failed to fully inflate, which would have been fatal in a real Mars mission. The program was discontinued before producing operational hardware, and the fundamental question of how to reliably deploy very large parachutes at supersonic velocities in thin Mars-like atmospheres remained partly open. SpaceX's Starship vehicle takes a fundamentally different approach to the mass scaling problem. Rather than using parachutes at all, Starship is designed to perform a supersonic retropropulsion sequence, essentially to slow down using only its rocket engines from hypersonic entry velocity to touchdown. This is sometimes called propulsive entry or retropropulsion landing. The approach sidesteps the parachute problem entirely by substituting rocket thrust for aerodynamic drag. The trade-off is propellant mass. Retropropulsion requires carrying enough fuel to provide the deceleration that the atmosphere and parachutes would otherwise supply. For a vehicle as large as Starship, this is a significant mass fraction. But Starship's architecture is designed around producing propellant on Mars, using locally extracted water and atmospheric carbon dioxide through a process called Sabatier synthesis or methanation, which would allow the vehicle to be refueled for the return journey. The landing propellant is thus not required to be transported from Earth, which changes the mass equation substantially. Some researchers are deeply skeptical that supersonic retropropulsion at the scale required for Starship will work as advertised in the Martian atmosphere. The physics of firing large rockets in a thin, dusty atmosphere during hypersonic flight are not well characterized at operational scales. The interaction between the retro-rocket plumes and the incoming hypersonic flow can produce complex shock structures that may destabilize the vehicle. The ground impingement effects when rockets fire near the surface, the ejecta of dust and small rocks thrown outward by the plume, can damage the vehicle or obscure the landing. Sensors. These are not hypothetical concerns. They are recognized engineering challenges that have been studied in wind tunnels and computational fluid dynamics simulations, but which have never been demonstrated at the scale of a crewed Mars lander. Other researchers, notably those affiliated with Elon Musk's Mars colonization advocacy, argue that the engineering challenges of supersonic retropropulsion are difficult but solvable, and that the development timeline for Starship's Earth landing operations will produce sufficient data to validate the Mars landing performance. There is genuine disagreement here, and the disagreement is not simply about optimism versus pessimism. It is about how much operational data from Earth analogs can be extrapolated to the specific conditions of Mars EDL. The answer to that question depends on how well characterized the differences between Earth and Martian atmospheric entry environments are, and, as we have seen, that characterization is incomplete. This is one of at least two places in the Mars landing problem where reasonable scientists and engineers hold fundamentally different views, and where the available evidence does not yet resolve the disagreement. Some researchers believe the atmospheric uncertainties are manageable with existing or near-term sensing and modeling capabilities. Others believe that the atmosphere's variability is deep enough that any crewed mission would require an extensive pre-certification program, dozens of robotic precursor landings at the intended site across multiple Martian seasons to characterize the local atmospheric environment before committing a crew to descent. That second view implies something quietly significant, that the cost of certifying a crewed Mars landing may be comparable to the cost of several complete robotic Mars exploration programs, not because the technology is beyond reach, but because the atmosphere demands a data foundation that takes decades and many missions to build. Patience, in the face of an incompletely characterized planetary atmosphere, may be the most expensive engineering resource Mars requires. Here, the false hope presents itself, clearly and attractively. The answer, it seems, might simply be to send better orbiters first. More atmospheric sensors, higher resolution, longer observation baselines. Build a more complete model of the atmosphere. Reduce the uncertainty. Make the EDL problem more tractable through improved knowledge. This sounds like it would work. It sounds like a clear path forward. A prerequisite program that, if funded and executed, systematically reduces the fundamental source of EDL risk. The answer seems obvious. Know the atmosphere better and the landing gets easier. But here is what that approach does not account for. The Martian atmosphere has been observed continuously from orbit since the Mars Global Surveyor arrived in 1997. The Mars Reconnaissance Orbiter, in orbit since 2006, carries instruments specifically designed to characterize atmospheric temperature, dust loading, wind profiles, and cloud formation. The Mars Climate Sounder instrument aboard MRO has produced a dataset of atmospheric observations spanning nearly 2 Mars years, nearly 4 Earth years of continuous measurement. Researchers, including David Cass and Armin Kleinbuhl at JPL, have used this dataset to develop increasingly sophisticated global circulation models for Mars. And yet, the atmospheric density encountered by landing vehicles still deviates from modeled predictions by amounts that can affect EDL outcomes. The dust cycle remains imperfectly predicted. Regional storms still develop on timescales that are difficult to forecast weeks in advance. The global dust storm of 2018, the storm that ended the Opportunity rover's 15-year mission by blocking the sunlight that powered its solar panels, was not predicted by any atmospheric model more than a few days before it began to intensify rapidly. It could not have been predicted with the atmospheric sensing capability that existed, because the storm initiated from a small regional event and grew through processes that the models did not fully capture. The hope that better orbital observations will reduce EDL uncertainty to negligible levels is, in practice, colliding with the reality that the atmosphere's variability is not simply a matter of insufficient data. Some of the variability appears to be genuinely chaotic, sensitive to initial conditions in ways that no finite observational system can fully constrain. If this is true, and some researchers believe it is, then a certain irreducible uncertainty in EDL atmospheric conditions will persist, regardless of how long humanity observes Mars from orbit or the surface. That hope collapses the moment you look closely at the dust storm data. Not completely. Better models do reduce uncertainty meaningfully, and that reduction is valuable. But the expectation that uncertainty can be reduced to near zero is not supported by decades of observation. Mars's atmosphere will remain partially unpredictable. Mars landings will remain, in some fundamental sense, a dice roll. A very carefully engineered, very thoughtfully prepared dice roll, but a dice roll nonetheless, in which one face of the die represents atmospheric conditions outside the model's prediction, and nobody knows before the roll how many sides the die has. This is where an honest accounting of the Mars landing problem arrives at something that the history of the field confirms repeatedly. The engineering community knows more than enough to attempt the next mission. They know how to build the aeroshell. They know how to size the parachute. They know how to design the terminal descent system. They know how to write the autonomous guidance software. They know most of what they need to know, but they do not know everything. They never have. And for 60 years, the gap between what they know and what the atmosphere actually does has been the space in which most of the failures have lived. The Perseverance landing in February 2021 was, by any reasonable measure, as well prepared as a Mars landing has ever been. The team had the accumulated knowledge of every previous mission. They had the terrain relative navigation system. They had a sky crane whose design had been validated by Curiosity. They had atmospheric characterization from MRO and MAVEN and InSight, the most comprehensive dataset ever available to an EDL team. And when the 7 minutes arrived, Adam Stelzner and his team in Pasadena still did not know, until the telemetry arrived 11 minutes late, whether the vehicle had survived. "I will be frightened all the way," Stelzner said before the landing. Not as a performance, not as managed humility for the benefit of the cameras. As a precise technical statement about a process whose outcome, despite the best preparation in the history of the field, remained genuinely uncertain. The fear was appropriate. It was earned by physics. It was the correct emotional response to a situation in which everything was prepared and nothing was guaranteed. The signal arrived. Perseverance had landed. The celebration that followed was not the celebration of people who had expected success. It was the celebration of people who had hoped for it, prepared for it, and known in the part of themselves that was honest, that preparation and hope were necessary but not sufficient. There is something here that reaches beyond engineering. It reaches into the question of what kind of knowledge is achievable, what kind of certainty is realistic, and what it means to attempt something whose outcome you can prepare for but cannot control. The Mars landing problem, at its deepest level, is not a problem that better engineering will fully solve. It is a problem that better engineering will make it more survivable, more repeatable, and more reliable, while leaving a residual uncertainty that belongs permanently to the atmosphere of another world. Take stock of where we are in this story. We have traced the cascade from entry angle to heat shield, to parachute to terminal descent, through the specific failure modes of each transition and the physical reasons they remain incompletely tamed. We have followed the mass scaling problem from Viking's 576 kilograms to Curiosity's 900 kilograms to the tens of metric tons that a crewed mission demands. We have seen the atmospheric double bind expressed in every phase of descent, and we have seen how the dust, that omnipresent Martian dust, compounds every other uncertainty. We have watched the gap between what the models predict and what the atmosphere delivers produce a history of failures that have no common cause except that they happened on Mars in the 7 minutes when nothing could be done. And we have arrived at a question that the engineering record alone cannot answer. Not a technical question. A different kind of question. One that sits underneath the physics and the software and the parachute dynamics, and has been quietly present in everything we have examined so far. Why do we keep trying? The answer is not simple, and it is not singular, and it will not be found in the mission requirements documents, or the EDL trade studies, or the atmospheric models. It will be found somewhere in the human response to the signal arriving from Jezero crater, 11 minutes too late to intervene, telling the people in Pasadena that the thing they built survived the thing they could not control. Picture yourself standing outside on a clear night, somewhere far from city lights. The kind of place where the Milky Way is not a suggestion, but a presence. A broad river of light from horizon to horizon, so dense in places that it looks like a luminous cloud. You can see it all. The core's amber glow toward the southern horizon, the dark rifts carved by dust clouds, the scattered individual stars bright enough to cast faint shadows. And somewhere in that sky, moving so slowly it barely registers as motion, a small reddish point of light tracks across the starfield. Not twinkling the way stars do, but steady and unwavering the way planets do. Mars. It does not look dangerous. It does not look like a graveyard. It looks, from this distance, like a jewel, warm-colored, quietly luminous, unremarkably beautiful, in the way that all planets are beautiful when seen from Earth. It has looked this way to every human generation that has watched the sky, from Babylonian astronomers recording its retrograde motions on clay tablets 4,000 years ago, to the first telescopic observers of the 17th century who strained to resolve its polar caps and dark markings, to the mission engineers who look at it now with different eyes. Eyes that know, behind the calm red point, a catastrophically thin atmosphere is lying in wait. There is a peculiar emotional quality to the moment after a major intellectual reckoning, when the weight of what has been understood settles from the mind into something more physical, more diffuse. The understanding does not disappear. It remains, but it is no longer fresh information demanding processing. It it has become something quieter, background knowledge, the kind of knowledge that changes how a familiar sight appears permanently without requiring conscious effort. If you have followed this story carefully here, that is what has happened to Mars for you. The red point in the sky is the same red point it always was. But you know now what it contains. You know the atmosphere. You know the 7 minutes. You know the chain of dependency, the sensor saturation, the parachute dynamics, the dust. You know the gap between what the models predict and what the planet delivers. And that knowledge, sitting quietly behind your perception of that steady red light, is not a burden. It is a kind of intimacy. You know Mars the way you know a person whose difficulties you understand, not as an abstraction, but as a specific, complex reality. Rest here for a moment. The technical material we have examined is dense, and it deserves this pause. Not because the story is over, it is not, but because the space between the knowing and the asking is important. The knowing has been about physics, about engineering, about failure modes and sensor architectures and atmospheric models. The asking is about something larger. Why does it matter that Mars is hard to land on? Not in the engineering sense. We know why it matters in the engineering sense, intimately. But why does it matter to you, listening to this in the dark? Why does the history of crumpled spacecraft in Martian dust carry any weight for a species that has never been to Mars, that may not go to Mars within the lifetime of anyone reading this, that has perfectly full and sufficient lives entirely unconnected to planetary entry dynamics? The answer, when you search for it honestly, is not what it first appears to be. At first, the appeal of the Mars landing story seems to be about triumph, about human ingenuity overcoming physical obstacles, about the image of engineers in matching blue polo shirts erupting in celebration in a room in Pasadena. That is a real part of it. The triumph is genuine, and it is worth celebrating. But triumph is not the deepest layer of the story, because triumph is not what the people most intimate with the problem report feeling most intensely. What they report, consistently, across missions, across decades, across success and failure, is something that sounds at first like humility, but is actually more precise than that. It is the experience of encountering a constraint that does not yield to will. Humans are accustomed, in the modern era, to the experience of problems that yield to sufficient effort and intelligence. A disease that cannot be cured today can often be cured tomorrow, given enough research. An engineering challenge that seems insurmountable often yields to a creative reframing, a new material, a new algorithm. The general trajectory of technological civilization is one of obstacles dissolving when enough smart people concentrate on them. This is not universally true, but it is true often enough to produce a cultural disposition toward optimism about tractability. The belief that hard problems are hard, not impossible, and that the distinction can always be resolved in favor of hard. Mars does not entirely share this disposition. The atmospheric double bind has not dissolved under 60 years of engineering attention. It has been managed, navigated, worked around. The sky crane is a genuine solution within the mass range where the sky crane works. But it does not eliminate the double bind. It lives within it. The communication delay has not been shortened. The speed of light has not been negotiated. The 7 minutes have not been compressed. The dust still swirls. The atmosphere still varies. The models still carry irreducible uncertainty. The most sophisticated EDL system ever flown still required Adam Steltzner to say, honestly, that he would be frightened all the way. This is not a failure of engineering. This is a feature of the universe. The universe contains constraints that do not yield, and Mars, sitting at its particular distance, in its particular orbit with its particular mass and atmospheric composition, is an exceptionally concentrated expression of several of them simultaneously. It is too close to ignore and too hard to dismiss as unreachable. It is just difficult enough to make every attempt feel nearly possible, and just unforgiving enough to make nearly anything different from actually possible, consistently and expensively, for 6 decades. There is a historical parallel here that deserves to be drawn carefully because it illuminates something that the engineering record alone cannot. In the early decades of the 20th century, a generation of aviators attempted to cross the Atlantic Ocean by air. The crossing was technically possible. The physics permitted it. But the accumulated difficulty of the attempt produced, in the years between 1919 and 1927, a litany of failures that bears a structural resemblance to the early history of Mars exploration. Between 1919, when the prize for a non-stop transatlantic flight was first offered, and 1927, when Charles Lindbergh completed the crossing, at least 6 pilots died in the attempt, and many more failed before reaching the ocean, or came down in it, or turned back when the conditions exceeded their preparation. What is instructive about this parallel is not the eventual triumph. It is what the failures reveal about the nature of the problem. The ocean crossing failed repeatedly, not because the physics was wrong, not because the aircraft were fundamentally misdesigned, but because the task required the simultaneous success of a large number of interdependent systems: engine reliability, navigation accuracy, weather prediction, pilot endurance, in an environment that was uncontrolled, partially unpredictable, and entirely unforgiving. Each failed attempt identified a specific failure mode. Each failure mode was addressed in the next attempt. The accumulated knowledge of all the failures made the eventual success possible. And then it was done. And then other people crossed the Atlantic routinely, within years, and the crossing that had killed a generation of aviators became a commercial proposition, managed by trained pilots following established procedures in designed aircraft. The hardness of the problem did not vanish. It was absorbed. The understanding that had been purchased at such cost was encoded into systems, procedures, regulations, and training programs that distributed the knowledge across an entire industry. Mars is at an earlier stage of that curve. The failures are still accumulating knowledge. The knowledge is still being encoded into better systems. The routine has not yet been reached, and for crewed landings, it is not yet clear that the routine will be reached within any timescale that feels near. But the direction is the same. The failures are not random. There is no evidence that Mars landing is impossible. They are evidence that it is hard in specific ways that require specific solutions, and that the solutions are being developed imperfectly and expensively and with significant human cost, in the same way that all genuinely difficult problems are eventually addressed. This parallel has limits, as all parallels do, and the limits are important. The Atlantic is 4,000 kilometers wide, and the crossing took 33 hours in Lindbergh's aircraft. The journey to Mars takes 6 to 9 months, and the planet is never less than 55 million kilometers away. The Atlantic has a dense, predictable enough atmosphere that meteorology can, within limits, forecast conditions days in advance. Mars has an atmosphere that remains imperfectly characterized after decades of observation. The Atlantic, if you go down into it, offers some chance of rescue. Mars offers none. The limits of the parallel point toward a discomfort that the Mars landing story ultimately cannot entirely resolve. The question is not whether humans can land on Mars. The engineering trajectory suggests that they can, eventually, with sufficiently advanced and sufficiently expensive systems. The question is whether the cost, measured in money, in time, in risk to human life, is commensurate with what the landing will return. And this is a question that the engineering record cannot answer, because it is not an engineering question. It is a question about values, about what a civilization chooses to do with its resources and its courage and its time. Some people answer it with the argument of survival, that humans must become a multiplanetary species to reduce the existential risk of remaining on a single world, and that this imperative makes the cost of Mars exploration not just acceptable, but obligatory. Others answer it with the argument of knowledge, that understanding Mars, its geology, its climate history, its potential for past or present life, is sufficiently valuable to humanity's scientific understanding that the cost is justified on intellectual grounds alone. Still others are less certain, and believe that the resources directed toward Mars landing would produce more human benefit if directed toward problems on Earth, whose solutions are more tractable and more immediately applicable. These are not engineering disagreements. They cannot be resolved by better atmospheric models or more reliable parachutes. They are arguments about what matters, and they will continue alongside the missions themselves, unresolved, as they have continued alongside every previous era of exploration. What the engineering record does tell us, clearly and emphatically, is that if the decision is made, if the choice is made to go, to build the vehicles, to accept the cost and the risk, then the problem must be taken with absolute seriousness at every stage and every level. Mars will not forgive the unit conversion error. Mars will not forgive the IMU saturation threshold that was set too high. Mars will not forgive the solar panel that was designed without a redundant deployment mechanism. Mars will not forgive the atmospheric density that the models said would be one thing and turned out to be another. These are not human failings in the ordinary sense. They are the expression of what it means to operate at the absolute limit of available knowledge in an environment that exceeds, at some point and in some way, whatever you thought you knew. The word terror in 7 Minutes of Terror is not an exaggeration, and it is not marketing. It is a technically accurate description of the subjective experience of people who understand precisely what is happening and cannot affect it. Terror is not irrational. It is the correct response to genuine uncertainty about the fate of something that 10 years of work and hundreds of millions of dollars and the careers of hundreds of people have been invested in bringing to this moment, and which now, for 7 minutes, belongs entirely to Mars. And here is the thing that is not often said directly, but which the history of Mars exploration encodes in every mission report, every failure investigation, every celebration that doubled as a release of held breath. The terror does not diminish with experience. Adam Steltzner had worked on Mars EDL for decades by the time Perseverance landed. He had watched Curiosity land successfully. He knew the system. He had designed it. He said he would be frightened all the way. Rob Manning, who has guided EDL development across 4 decades of Mars missions, has described the day of landing as the one day every year he wishes he had chosen a different career, said with love and dark humor and the precision of someone who means it exactly as much as it sounds. This is not a weakness. This is knowledge. The people most frightened on landing day are frightened because they understand the most. Fear is a function of comprehension. It is the precise emotional analog of the technical uncertainty, a measure of how much is at stake and how little control remains. Hold that image. The room in Pasadena, the screens showing telemetry, the engineers in their polo shirts, the the families and guests watching from the back, the cameras broadcasting to a waiting world. The signal delay is counting down, and in the room, the knowledge that whatever happened, it already happened. 7 minutes ago, on a planet 200 million kilometers away, the vehicle either survived or it did not. The information is traveling toward them at the speed of light. In the room, there is nothing to do but wait. That waiting room, in its quiet and its tension, is one of the most honest places humans have built. It is a place where the gap between human ambition and the indifference of the physical universe is as narrow as it ever gets. A room full of people who tried everything they knew and now wait to learn whether everything they knew was enough. Sometimes it is, sometimes it is not. And in both cases, the universe responds without commentary. Think about what it would mean to be in that room as a member of the human species, not as an engineer. To stand behind the engineers and watch the numbers on the screens and understand that what is being measured is the outcome of humanity's longest-running dialogue with the fact of its own smallness. 60 years of attempts, dozens of spacecraft, billions of dollars, careers measured in decades, and the atmosphere of Mars, thin as it is, thin enough that you could almost call it nothing. That atmosphere has been the decisive factor in more outcomes than any single engineering decision, more than any budget choice, more than any organizational failure. The atmosphere simply is what it is. It does not adapt to the spacecraft. The spacecraft must adapt to it. There is a philosophical tradition stretching back through the Stoics and the Buddhist thinkers and the medieval naturalists and the early scientists that holds a particular kind of reverence for what does not yield to human will. Not worshipping it, not despair in its face, but a specific earned respect. The recognition that the universe contains things that are not problems to be solved, but facts to be understood, and that understanding them is itself a form of relationship, a kind of intimacy even. The Martian atmosphere in this light is not simply an engineering obstacle. It is one of the universe's permanent facts. A thin, cold, dusty layer of mostly carbon dioxide that has been there for 4 billion years and will be there for 4 billion more, doing exactly what thin, cold, dusty atmospheres do when something falls through them too fast. It does not intend to kill spacecraft. It does not prefer failure to success. It is simply what it is, and what it is happens to be, precisely, comprehensively, exhaustively difficult for the things humans want to do there. To understand that, fully and without consolation, is to arrive at something that feels like sadness, but is not quite sadness. It is the feeling that accompanies the recognition of something true that is also irreducible, that cannot be resolved into something easier or more comfortable. The universe is vast, and we are small, and the distance between our ambitions and our capabilities is not closing as fast as our ambitions are growing. Mars is hard. It will remain hard. And that hardness is not a challenge that humanity will eventually surpass, in the way that it surpassed the challenge of crossing the Atlantic. It is a challenge that humanity will learn to navigate, case by case, mission by mission, with each navigation costing more than the last, and each success belonging fully to the people who earned it and to the machines that survived. This is not a reason to stop. It is a reason to be honest about what continuing means. It means accepting a failure rate that would be unacceptable in any other domain of human activity, because the problem is not one that normal standards of engineering margin can fully contain. It means accepting that human lives, when the crewed missions come, will be at risk in ways that cannot be fully quantified, because the atmosphere's uncertainty is irreducible and the consequences of an EDL failure are total. It means accepting that the knowledge gained from failure, the failure investigation reports, the lessons learned documents, the redesigned sensors and updated software, is itself a kind of tribute to the people and resources lost, and that this tribute is the only form of recovery available after a spacecraft crumples in Martian dust. The Soviet engineers who built Mars 2 and Mars 3 in the late 1960s were not careless people. They were gifted engineers working under extraordinary pressure in a program that demanded results on a political timeline. Mars 2 hit the planet and created a crater. Mars 3 transmitted for 20 seconds. The knowledge gained from those failures contributed in ways that are difficult to trace precisely, but are real to every subsequent understanding of what Mars EDL demands. The wreckage of Mars 2 is still there, somewhere in the northern plains, the first human artifact on another planet, rusting, if iron oxide can be said to rust further on a planet that is already rust, embedded in the ground of a world it was sent to explore. It is still there. Every spacecraft that has ever been sent to Mars and failed to survive landing is still there. The Martian surface is a museum of human attempt, a geological record of ambition and overreach, and near miss and unexpected failure, preserved by the same cold, dry, airless quality that makes Mars so inhospitable to the living. They do not decay the way they would on Earth. The metal oxidizes slowly. The plastic and polymer components may persist for thousands of years. In some distant future, if humans ever walk on Mars, they will find these artifacts: the broken landers, the scattered parachutes, the heat shields lying where they fell. And they will understand them as the price of arrival. The price of arrival. That phrase captures something that the engineering analysis alone cannot. Every successful Mars landing was preceded by failures that refined the understanding that made the success possible. The Viking landers succeeded partly because Mariner 4 and 9 had characterized the atmosphere they would descend through. Pathfinder succeeded partly because Viking had demonstrated what a Mars landing demanded. The Mars exploration rovers succeeded partly because Pathfinder had validated the airbag approach. Curiosity succeeded partly because every previous attempt, successful and failed, had informed its extraordinary engineering. The price was paid in wreckage and lost missions and human disappointment, and the payment purchased the knowledge that the successes required. This is the structure of all genuine exploration, not the triumphant narrative of steady progress, but the actual structure, failure as the primary mode of learning, success as the exception that justifies continuing, and the accumulating record of both as the foundation on which future attempts are built. It is not a comfortable structure. It offers no guarantees. It does not promise that the next mission will succeed, or that the investment will be recovered in proportion to its magnitude, or that the human lives risked in crude missions will come home safely. It offers only this: that the attempt is being made with the fullest knowledge available by people who understand what they are doing, on behalf of a species that has, from its earliest moments, moved toward the horizon rather than away from it. Not because the horizon guarantees anything, because moving toward it is what the species does. Because the red point in the sky has been there for every human generation, and every human generation that has looked at it has felt, in some form, the pull. Everything we have examined comes back to a single, stubborn, beautiful fact. Mars is there. It is there right now, in the sky above wherever you are, on the other side of whatever hour this is, past the atmosphere that keeps you warm, past the moon that keeps the seas regular, past the orbital distances that make the inner solar system the neighborhood it is. It is there with its butterscotch sky and its iron-red plains, and its whisper of an atmosphere that has been quietly defeating spacecraft for 60 years. It is there whether humans decide to go or not, whether the funding holds or collapses, whether the engineering problems yield or persist. Mars does not require human attention to continue being exactly what it is. It has been exactly what it is for 4 billion years. And what we have learned through 6 decades of attempts is this: the most precisely, specifically, comprehensively difficult landing destination that humanity has yet seriously tried to reach. Not because it is the most extreme environment in the solar system. It is not. Venus is hotter, the gas giants are more massive, Europa's ice shell is thicker, the vacuum between the stars is more absolute. But those places are extreme in ways that are, at least in the short term, obviously impossible. Nobody is building a lander for the surface of the sun. The impossibility is clear and the attempt is not seriously made. Mars is different. Mars sits in that precise sweet spot of almost possible, precisely difficult. The atmosphere is almost thick enough for parachutes to work, but not quite. The distance is almost close enough for real-time communication, but not quite. The gravity is almost weak enough to make retropropulsion tractable, but not quite. The landing sites are almost well characterized enough for confident targeting, but not quite. Every almost in that list is an engineering problem, and every engineering problem has driven the development of a new solution, and every new solution has added complexity to the landing system, and every new complexity has introduced new failure modes, and every new failure mode has eventually been expressed in a mission that did not survive. The pattern will continue. The next Mars lander, whatever it is, wherever it is built, for whatever agency or private organization funds it, will face the same atmospheric double bind that Viking faced in 1976. The communication delay will be the same speed of light limitation. The dust will be there. The 7 minutes will be there. The fundamental physics of the problem is fixed, and it will remain fixed, and the engineers of the next decade and the next century will be working within the same constraints that the engineers of the last 6 decades have worked within. They will be smarter, better equipped, operating with more data and better models and more capable computers. They will also be on Mars, and Mars will be what Mars is. This is not a cause for despair. It is a cause for a different kind of respect than the triumphant variety. A quieter, more durable respect for the work, for the people who do it, and for the planet that makes it necessary. Think back to where this story began. To the graveyard, Mars 2, Mars 3, Mars 6, Beagle 2, Schiaparelli, Polar Lander, Deep Space 2. Names that ended in silence. Names that represent, in the aggregate, the tuition humanity paid to learn what landing on Mars requires. Each of them was built with the best knowledge available at the time. Each of them failed in a way that was not fully anticipated. Each of them taught the people who came next something that could not have been learned any other way. The failure of the Mars Climate Orbiter in 1999, lost to a unit conversion error, taught an entire generation of engineers that the institutional discipline of unit verification is not a bureaucratic formality, but a mission-critical function. The report from that investigation changed how space programs manage software interfaces between contractors. Not just for Mars missions, for all missions across all agencies. The wreckage of a $125 million spacecraft purchased a permanent change in the culture of aerospace software engineering. The failure of the Schiaparelli lander in 2016, lost to 1 second of IMU saturation, taught the EDL community that autonomous system architectures must account for sensor failure modes that produce coherent but wrong signals. That the hardest failures to detect are not random noise failures, but systematic failures that look internally like valid data. The investigation report from that event has been incorporated into the design philosophy of every subsequent European Mars mission and into the thinking of engineers at JPL and elsewhere who were watching closely. The 20 seconds of Mars 3 in 1971 are themselves a kind of knowledge, not a clear knowledge, not a knowledge that yielded a specific engineering lesson, but a knowledge about the depth of the unknown. Something ended Mars 3's transmission. The most likely candidate is electrostatic discharge from the global dust storm. But we do not know with certainty. We do not know with certainty, 50 years later, exactly what killed the first spacecraft to survive a Mars landing. That residual uncertainty is itself informative. It tells us that Mars is capable of producing failure modes that remain undiagnosed even after sustained analysis, and that this capability has not diminished. The successful missions are equally part of this record. Viking's 6 years of operation produced atmospheric and geological data that informed every subsequent mission's understanding of the surface it was targeting. Pathfinder's airbag bounce across Ares Vallis in 1997 validated a landing approach for lightweight payloads and demonstrated that the Martian surface, at least at that location, was navigable by a small-wheeled vehicle. Spirit and Opportunity, the twin rovers that landed in January 2004, each designed for a 90-day mission, operated for years. Spirit for 6 years, Opportunity for 15. Revealing a geological record that transformed our understanding of Mars's wet, ancient past. Curiosity, still operating in Gale Crater as these words are written, has spent over a decade climbing the central mountain of that crater, reading billions of years of Martian climate history in the layered rock. Perseverance in Jezero Crater has collected samples that are planned, pending the outcome of a deeply complicated and not yet resolved Mars sample return mission, to be the first Martian material ever brought to Earth. Each of these successes was paid for by the failures that preceded it and refined it. Each represents the accumulated knowledge of an entire program, encoded into a vehicle that was asked to fall through the worst atmosphere in the solar system for precision landing, and survived. Each represents the work of hundreds of people over years and decades, working within the constraints that the universe imposed and the budget that civilization provided, producing something that landed safely on the surface of another world and then went to work. That is the sentence that deserves to sit with you for a moment. Landed safely on the surface of another world and then went to work. There is something in that phrase that exceeds its technical content. The machines that survived Mars EDL did not simply survive. They became, for the duration of their operational lives, outposts of human curiosity on an alien surface. Instruments extended across an impossible distance, sampling and imaging and measuring a world that no human has ever touched. Every photograph returned from Mars, every atmospheric reading, every rock analysis, every wind speed measurement was produced by a machine that had to survive the 7 minutes first. Science exists because engineering is held. The science has been extraordinary. We know now that Mars once had liquid water on its surface, possibly for hundreds of millions of years. We know that it once had a magnetic field that protected its atmosphere from solar wind erosion, and that the loss of that field is closely linked to the thinning of the atmosphere that now makes landing so difficult. We know that the ancient Martian climate was warm enough and wet enough to be potentially habitable, that the mineral signatures of past water are preserved in the rock of Gale Crater and Jezero Crater, and dozens of other sites examined by rovers and landers. We know that the Martian subsurface may contain water ice accessible to future explorers, and that the water ice deposits at the poles represent a resource that a future crewed mission might use. We know all of this because of the machines that survived the 7 minutes. The knowledge does not stand apart from the engineering that delivered it. It is inseparable from the atmospheric double bind, the sky crane, the disc gap band parachutes, the Pika heat shield, and terrain relative navigation. Science was purchased by engineering, and the engineering was educated by the failures. And the failures were the inevitable cost of attempting something that the universe had not made easy. Here is the final reframing, the one that the entire story has been building toward. Mars is hard to land on. That is not a temporary condition, not a problem that is about to be solved, not a challenge that the next generation of engineers will simply surpass. It is a permanent feature of the relationship between the human species and the fourth planet. Mars will always be harder to land on than the Moon. It will always be harder to land on than returning capsules to Earth. It will always sit in that precise zone of almost possible but not quite easy, demanding from every mission a level of engineering discipline, atmospheric knowledge, and autonomous system reliability that pushes the current state-of-the-art to its limits. And because it is hard, because it genuinely resists, because the planet does not simply yield to ambition and intelligence and engineering sophistication, because the atmosphere is what it is, and the 7 minutes are what they are. Every successful landing carries a weight of meaning that an easy destination could never generate. The celebration in the JPL control room after Curiosity landed was not disproportionate. It was exactly proportionate. It was the correct magnitude of joy for the magnitude of the difficulty overcome. The tears were earned. The embraces were earned. Every moment of that celebration was purchased by the specific, detailed, technically precise understanding of everything that could have gone wrong and did not. And the next mission will earn its celebration too, if it succeeds. And the mission after that. And the first crewed landing, whenever it comes, in 20 years, in 30, in 50, will be the most earned celebration in the history of space exploration, because the people who make it will know, more precisely than any previous generation, exactly what they survived. They will have a complete failure record. They will have Schiaparelli's second and Mars Polar Lander's leg sensors, and Mars Climate Orbiter's unit conversion, and Mars 2's entry angle, and Mars 3's 20 seconds and all of it. The full curriculum of what Mars charges for the landing fee. And they will have paid it, and survived, and stood on the surface that has been waiting for them for 60 years. The red plains will be quiet. The butterscotch sky will be present in every direction, fading at the horizon to a darker tone. The sun will be smaller than they expected, casting its crisp shadows on the ancient rust. The wind will be blowing, probably. Mars is almost always windy somewhere, carrying fine particles of iron oxide that will settle on every exposed surface within hours. The temperature will be cold in ways that the suits will manage, but the mind will register. And somewhere above, the abandoned descent stage will have already crashed half a kilometer away, its job complete, its complexity spent, its 7 minutes of purpose over. The graveyard that greeted us at the beginning of this story, the wrecked spacecraft scattered across the Martian plains, will still be there. Mars 2, Mars 3, Beagle 2, Schiaparelli, all the others, preserved in the cold, dry air, undecaying. They will be visible from orbit to the crew now standing on the surface. They are not only wreckage, they are the foundation. They are the education. They are the price of the landing that made this moment possible. More than half of every machine humanity has ever sent to the surface of Mars lies broken across its red plains. That is the number we began with, and it has not changed. It will not change. History is history. But what has changed if this story has done what it set out to do is what that number means. It is not a record of failure. It is a record of learning. It is the accumulated tuition of the most difficult applied physics problem that humanity has yet seriously attempted, paid in hardware and time and money and the careers of brilliant people over 60 years on behalf of the question that has animated every launch. Whether the thing we built is good enough to survive what Mars does to it. Sometimes it was. Sometimes it was not. And in both cases, something was learned that could not have been learned any other way. If this changed how you think about the red point in the sky, then the time was well spent. The engineers who gave their years to this problem, the ones who succeeded and the ones who didn't, the ones who cried in the control room and the ones who watched their telemetry go silent, they deserve to have the difficulty of their work understood completely and without softening by the people on whose behalf they were working. That is us. That has always been us, looking at the sky, feeling the pull, and occasionally, at enormous cost, finding a way to go. Thank you for staying with this.